This video will be an introduction to the digital design tool Logisim. What we saw in our previous video was digital design using AND gates, OR gates, and NOT gates. We also saw a simple example. We will redo that simple example using Logisim. To use Logisim, first we need to access and download it. I will show you how to do that. Next, I will show you how to use the menu to actually do the design. We will do a more difficult problem, one that has an implication operator in it. And finally, I will show you about an application for digital design, namely lighting up one particular segment of a 7-segment digital display. This is the home page for Logisim. We see here this command right here that says download Logisim. If we click on it, we go here and we see the commands for doing the downloading. Notice that there is both a Mac version and a Windows version. If you click on the appropriate Mac or Windows file to download, after it downloads, it will then be ready to use. To remind you of that, we need to download the code. We go to the home page for Logisim. Then we clicked on Download Logisim. Then we clicked on the sourceforge.net page to actually do the downloading. The program should install itself. Together with the program, under the Help button, there's a very nice basic tutorial that you might want to look at. Now, let's do an example, the example we had from the previous video. This is the design that we built. Let's look at it again. We have P and not Q or R. Once again, we take Q, we need to negate it. We conjunct that using this AND gate with P. Then we take the output of that and OR it with an R to get the final expression P and not Q or R. Now let's build it in Logisim. Here we are in the main screen of Logisim. This is our work area here. These are the commands that we will be using. The first one is a toggle finger right here. We will change things from true to false values on our inputs using it. Sometimes we will want to label things. We will do that with this text button right here. Inputs will be marked with the square. Outputs will be marked with the circle right here. And finally, you see the 3 gates that we'll be using, namely the inversion gate, that is the NOT, the AND gate, the conjunction, and finally the OR gate, the disjunction. So let's do the simple example that we did in the previous video. Recall that's P and not Q or R. I will start by just putting the NOT right here and I will hook it up to an input, and I will call that input Q. I will take the output of that and I want to push that through an AND gate with P. So pull out the signal right here, put an input right there, and label that one P. So what's coming out now from this AND gate is P and not Q. Good. To finish this then, what we need is to OR that, disjunct that, with R. So I will go get my OR gate right here. I will turn a corner right here so things aren't quite so crammed. I will put another input here, namely R, and label it such. And we see we have now coming out P and, not Q, or R. That's the one we wanted. Now, let's put a output on final version right here, and notice the 0 in the output. In digital logic, you should read zeros as false values and ones as true values. So we see here that if we had inputs of 0, 0, 0, remember, read that as false, false, and false, the output should be false. Now we can follow that also through the lines right here, because a dark line is going to indicate a 0, and a light green line will indicate a true. So here we have, starting with 3 falses, 3 zeros, everything comes till we change the value of Q, it gets inverted to a true, but when we AND that with a false, we still get a false coming out of it. We OR that with the false in R, and we still get a false right here. But let's use the toggle up here, the finger, and change something. Let's change the value of P. So now P is true. Now going into the AND, we have P being true and not Q being true, because Q is false. That comes out as a true, that is ORed with R, and of course true or false yields us a true. So now you see the output has a 1 in it, indicating a true. We can toggle some other things. For example, let's change Q to a true, but now we have not Q then is false, so coming out of the AND gate is a false. So the 2 inputs to the OR gate are false and false, therefore the entire output of the system will be a false. And you can go through here and change to all 8 values of the trues and falses for P, Q, and R, P having 2 different states, Q having 2 different states, R having 2 different states, and you can check them to see what the output is for each one of those 8 situations. Now let's do a more difficult problem. This one says R and P or Q implies R or P. The first difficulty we have with this one is that the digital design tools don't have an implies gate. They only have ands, ors, and nots, plus some other things such as NOR and NAND that we're not going to use. The important thing is there is no implies gate. Nevertheless, we know using the logical identity conditional disjunction that we can convert from an implies to something only involving ands, ors, and nots. Let's do that at the beginning. We take the original expression and we realize it's the same as the negation of the antecedent together with the disjunction of the consequent. That is, since antecedent implies consequent is the same as not antecedent or consequent, we have here not R and P or Q, that is the antecedent, or R or P, the consequent. This is nice because this version right here uses only nots, ands, and ors. Those are the gates we have. We don't have an implies gate. Once again, this is the expression that we want to embed in our logical design. All right, the expression begins with R and P or Q. So let's start with just those. We will take an OR gate and we will hook it up to inputs P and Q. I will label those P and Q. So, coming out of this is P or Q. Now we need to AND that with an R. So I'm going to turn a corner right here so things aren't too pushed together. And I will add an input R right here. Now, so far we have the expression P or Q and R. Now, in our situation, in our problem here, we need to negate that. So let's get this knot right here and stick it in. Now we have the negation of that. Our expression also had this output being ORed with R or P. So let's do that. We're going to take P and just pull it on down from our previous version, and we're going to use that together with R, and we said that we're going to disjunct these. So there we are, and now we take P or R, and we're going to disjunct that with the negation of the sub-expression P or Q and R. And that's our output. See this little piece right here? We can just remove it. It doesn't hurt anything. But we now have our output. Now notice, our three inputs are all zeros coming in false, but our output here is true. And we can work through this and see why that is the case. But let's toggle on some of the inputs. We will know there's 8 possibilities for P, Q, and R. So let's just change P, and we see things in our design have changed, but the output is still 1. Let's change Q to true. And you see other changes. Output is still true. How about if R were true? Again, changes, but the output is still true. Let's keep changing things. Let's change Q back to false. Some things have changed, but the output is true. Change Q. Again, changes, but the output is true. In fact, if you were to go through all 8 possibilities of the inputs, the output is always true. In other words, we've had a logical design to show that that expression is a tautology. For any values of the inputs, the output is always true. The last thing I'd like to show you is an application of digital design tools, namely a 7-segment display. It looks like this in a small version. You see these on digital watches, you see them on your television, you see them on microwaves, you see them in large versions on scoreboards at football games. Now, you see some pins right here leading up to something on the front face right here. This pin right here applies to this decimal point right here, and we're not going to use that in our example. Also, this pin right here actually connects to power, and we're not going to use that either, but we will use the other 7 pins. This is what it looks like. Here are the 7 pins that we're going to be using, and they hook up to these display elements right here, the 7 display elements. If we wanted to represent a 1, we would want to turn on this element and this element, and you see those segments are shown here, and that would give us a 1. We'd have to have inputs to the B and the C, both B and C, to get that properly lit. If we were to represent a 3, we need not only B and C, but you also need A, G, and D. So you see we now have inputs to A, G, and D. How about if we wanted to show a 6? Now we don't need B anymore, but we do need all of the other elements connected. Finally, if we wanted to show a 7, we see we need these 3 segments right here lit. All right? Suppose we had the problem of just seeing when the F segment should be turned on, when it should be lit, if the inputs were representations of the numbers between 0 and 7, just 0 and 7. You need to light the F segment. Now, which ones of our digits between 0 and 7 actually should turn on the F segment? Well, we see 0 is going to need the F segment, but 1 is not, nor will 2. 3 doesn't need the F segment either, but 4 does, so does 5, so does 6, but 7 does not. We need to turn on the F segment just for the numbers 0, 4, 5, and 6. The input, however, is going to be encoded in 3-bit binary. So a 0 will then be represented as 0, 0, 0. 4 will be represented 1, 0, 0. 5 will be 1, 0, 1. And 6 will be 1, 1, 0. To make sense of this, let's call the early digit P. So P is the leading bit. Q will be the middle bit, and R will represent the trailing bit. Now, using this way of representing things, a 0 could be thought of as not P and not Q and not R. A 4 will be a P and not Q and not R. A 5 will be P and not Q and R. And finally, a 6 will be a P and Q and not R. So we're using a binary representation of these numbers right here, and then we've rendered that in a logical expression over here. Now let's look at this for a moment. If any of these 4 cases hold, then we need to light the F segment. So we want to disjunct these 4 expressions, but notice that each of these 4 expressions is itself a conjunction, sometimes with an original value of an input, sometimes with a negated value. The final expression, once again, is the disjunction of the 4 conjunctions of our inputs, sometimes in their original forms, sometimes in their negated forms. So this is the design that we would end up with. This is actually the output of Logisim that I used to implement this right here. It hooks to the pin that controls the F segment right here. Let's look at it slowly. We have inputs P, Q, and R. Remember, those are the encodings of the numbers that we have between 0 and 7. We take those signals. Sometimes we negate those. Sometimes we do not. Then we have this bank of ands and a final disjunction. Let's look at it sort of backwards, hooking up to the pin that controls the F segment is a disjunction, an OR gate of 4 expressions. So we see the 4 coming in here. Now, let's look at one of them. Let's look at this one right here. It represents this sub-expression. Notice it's supposed to have a not P ANDed with a not Q ANDed with a not R. Let's check that. Here we have, coming back, not P. Good. How about this one? Going back, we see not Q. And finally, this one, working backwards, we see negation of R. Good. So that does implement not P and not Q and not R. Let's just do one other one. Here we have P and Q and not R, and that's this AND gate right here. Its first input is, walking backwards, P, good. Its second input is Q, that's good. And its third input is the negation of R, and that's what we want as well. So this expression right here we came up with, that's the expression that should control when the F segment of this 7-segment display should be turned on.